So in a phenomenological mathematical theory of plasticity, uh, we have a phenomenon which is the uniaxial stress strain test, where there is only one component of stress that is present in the material. The material is shaped in such a way that there's only one component of stress present, and we routinely conduct these uniaxial tests. Now we are trying to generalize this to a situation where there is a full state of stress at a point. In other words, equivalently, there are three principal stresses: sigma 1, sigma 2, sigma 3. And when this is the situation, we try to frame a three-dimensional phenomenological theory. And the test for that theory is that when it's reduced down to one dimensions, it should follow whatever we see in the experiments. The first example of the generalization is the yield condition that we have discussed. Both Tresca and von Mises are framed in such a way that they uh, degenerate to the uniaxial stress strain curve when there is only one component of stress. Obviously, this generalization is not unique. You can do it in different ways, and different materials demand that you do it in different ways. So we have different kinds of yield functions. Now, what we are going to see is how other aspects of the uniaxial stress strain response that we have seen are generalized to three dimensions. Though the generalization is not unique, there are some rules, there are some logical arguments that the generalization must follow, and we will look at that. We have already seen some of those arguments. One is the argument of isotropy, which leads to some symmetries in the yield, in the shape of the yield function. We are going to see a few more. We will work mostly with the von Mises yield condition. So I have drawn the von Mises yield surface in the principal stress space. So the von Mises yield surface is a cylinder in the principal stress space. And this is how what I'm going to show you now is how we imagine the yield surface to behave as we load the material. So this is a state of stress completely inside the yield surface. So this region inside the yield surface is the elastic region. This region is the elastic region. So this stress is an elastic stress. So this stress will be defined by its three principal values, and this stress is an elastic state of stress. When also the axis of this cylinder is the hydrostatic axis, which is defined by sigma 1 equal to sigma 2 equal to sigma 3. Now, when this stress state hits the yield surface, we have the possibility of plastic yielding. So yield condition has been satisfied. Now, when the yield condition is satisfied, we can also have a normal to the yield surface, an outward normal to the yield surface at the point at which the stresses hit the yield surface. And the current yield stress is in uniaxial tension, it's equal to sigma y. Now, we can have several situations from this. One is we have reached the yield surface, and now we want to give a small increment in stress d sigma, and this increment is such that n dot d sigma, so this angle here, is greater than 90 degrees, so that n dot d sigma is less than 0. When n dot d sigma is less than 0, it means that this point is trying to go inside the yield surface, which means that this is a situation of elastic unloading. This is a situation of elastic unloading. Why unloading? Because it has already been loaded to plasticity in the previous step, and in this step it's trying to go inside, so it's trying to unload. So this is an example of elastic unloading. Remember, in the uniaxial curve we had this plastic loading and then elastic unloading was parallel to the initial slope. So that is what we are trying to simulate in this 3D simulation, 3D situation. So this is elastic unloading. If d sigma is outward, so that n dot d sigma is greater than 0, then plasticity of course happens. This is plastic loading. Okay, if plastic loading happens, then we can divide d sigma up into two parts. One is along the hydrostatic axis. We already know that this part does not play any role in plasticity. And then there's this other part, which is the deviatoric part of d sigma, which is what is driving plasticity. Now, if it's a work hardening material, we imagine that this yield surface will now expand. Remember, if you unload and then load again, your apparent yield stress now will be this and not the initial yield surface. So this was your initial yield value, and now since you have loaded the material in the first step and then you unloaded and then you are trying to load again, it is as if your yield value has increased, and the yield value here in the three-dimensional situation will correspond to the radius of the circle, and the radius increases, and the radius will increase according to how much deviatoric stress you have given. So this will be your new yield surface now for a work hardening material. If the material is perfectly plastic, if the material has a stress strain, uniaxial stress strain relation of this, the expansion of the yield surface will not happen. But for a work hardening material, the expansion of the yield surface will happen. So this is how it will be for what is known as an isotropic hardening situation. There are other kinds of hardening. Isotropic hardening is the situation in which your yield stress in tension and compression are the same. So whatever we are discussing, the symmetry of the yield surface, etc., are for isotropic hardening. But there are other kinds of hardening like kinematic hardening and mixed hardening, which we are not discussing, which are not relevant at this moment for our purposes. Now, if you look at the stress strain curve, uniaxial stress strain curve, there are several regions in the uniaxial stress strain curve. For example, there's this elastic region, and then in this region, after you have crossed the initial yield point, in this region, you have plastic loading, and epsilon p dot is always greater than 0. And in the compression branch, epsilon p dot is less than 0 after this yield is reached. After initial yield is reached and you keep loading the material, you will have plastic strains building up. So epsilon p dot will be greater than 0. Now, in this region, as well as in this region, the material is hardening. So when the material is hardening, your rate of increase of stress is positive. Rate of increase of plastic strain is also positive, so that the product of the two is also positive. In this region, this is negative. Rate of change of stress is also negative. So this is valid for both these regions. So this is the signature of hardening when sigma dot and epsilon dot, the rate of change of both are the product is greater than equal to 0, which means that d sigma d epsilon p is greater than 0. Okay. Now, in this region, you have perfect plasticity. This is a region of perfect plasticity where sigma dot is 0, but epsilon p dot keeps increasing. So this is a signature of perfect plasticity. And in this region, sigma dot decreases when epsilon p dot increases. So this is what is known as a softening region. So we will assume from now on that such softening regions do not appear in the stress strain curve of the material. So we have what is known as a stable material which obeys this inequality. So this is the basis of an important postulate that we are going to now discuss, which is called the Drucker's postulate. So Drucker's postulate defines a work hardening or a stable material as one that obeys this relationship in 3 dimensions. What I had shown you here is in 1 dimension, and in general, Drucker's work hardening material has to obey this. If it does not obey this, then you have a softening material, and that is outside the purview of what we are going to talk about. Okay. Now, of course, your total strain is elastic strain plus plastic strain, but sigma times the elastic strain is always positive. So I can add, I can write this, I can multiply by sigma both sides. And if this is greater than 0, this is greater than 0 anyway, so this is also greater than 0. So this can be equivalently written as, for a stable material, the d sigma ij times the total strain is always greater than 0. So this is a stable material. So this is not a thermodynamic principle. It is actually an expression of the phenomenology that we see from 1D experiments. Okay, so Drucker's postulate can be written in a different way as well. So this, please remember this form and this form. This will be important for us. We will also write it in a different way. So the different way is, let's look at it in 2D. So this is a 2D stress strain curve, von Mises. Sigma 3 is equal to 0, then it reduces to this ellipse. We have done this before. Now imagine that we have a stress state that is deep inside the elastic region, and this stress state is called sigma star, and then we follow some path, we vary the stresses sigma 1, sigma 2 in some way, and we reach a stress state on the yield surface. So we have yielded at this point. So we yield. After reaching the yield surface, we load the material for some time, and then we are trying to increase the stress from sigma to d sigma. So in this process, we will have a d epsilon p, which is the plastic strain increment. So if you now, after reaching the yield surface, if you want to increase the stress, you cannot do it by increasing the elastic strain only. You have to increase the plastic strain, and your total strain now will be elastic plus plastic. Okay, and in the process, for a work hardening material, your yield surface will also shift to the tip of the point where up to which you have increased the stress. So your yield surface will follow the stress path, the tip of the stress path. Okay, now imagine that I unload it back. And if I unload it back, I unload it back to the, when I unload it back, I unload it back to the initial sigma star. Now in this process, in this entire process, since you have incorporated plasticity, since d epsilon p was accumulated inside the material, you must necessarily have the total work done in the whole process must be positive. So a total work done in the cyclic process must be positive. What have we done? So let us take sigma ij minus sigma ij star times d epsilon ij, and that d epsilon ij can be broken up into d epsilon ij e and d epsilon ij p. This first term is cyclic in nature. So when you unload the material, when you come back to the same state of stress, this will be gone. So this will be 0 in a cyclic process, but this will not be 0. And Drucker's postulate, another form of Drucker's postulate, states that the cyclic integral of this vector connecting the state of stress on the yield surface to any state of stress inside the yield surface must always be greater than equal to 0. So if you if you now want a more rigorous, stricter condition, you can have the condition that this quantity is always greater than 0, in which case it will ensure that the cyclic integral is also always greater than 0. So this is the Drucker's postulate. This is another form of Drucker's postulate, which says that if you undergo plasticity in a cyclic process, as part of a cyclic process, then you must do non-zero work. You must do non-zero work in a cyclic process which involves plasticity. This is just another way of saying that plasticity is a irreversible process, and therefore to go through it, if you have plasticity in your process, then you must be dissipating energy. Okay, so this is what it says. This is the loser condition, and a stricter condition is this. If this condition is valid, this condition is obviously implied, but not the other way around always. Okay, so let us take this this stringent condition, and let us also remember oh, I'm doing something wrong. Let us also remember these two conditions. Okay, and now using these two principles, using either using this and this, we can now arrive at a few postulates about the shape of the yield surface. Now, I will try to show this in a rather informal way, not very rigorously, but they are valid for they can be rigorously proved as well. So think of it like this. So we have these state of stress inside. Go increase the stress, hit the yield surface, cause yield. Then we are trying to increase the stress even more. So we incur plastic strain. The yield surface moves. We come back to the original point. This was our cyclic process. Now in this process, we must have this conditions always satisfied, never violated, and this condition also always satisfied, never violated. So now imagine that I have drawn a close-up of this part of the yield surface. So this is the yield surface. This is the normal to the yield surface. So this is the normal here, and then this is a stress state inside the yield surface, the elastic stress state, and this is a stress state on the yield surface. Now assume that you have incurred some plastic strain while increasing the stress by d sigma, and that plastic strain tensor, or the principal components of that plastic strain tensor, are plotted in 3 dimensions, in this case in 2 dimensions, on this same plot. So this is your plastic strain tensor, principal values of the plastic strain tensor, which in this case is 2 components. And then if this is the plastic strain drawn on the same plot, and your d sigma lies in this triangle, which is the triangle between the tangent to the surface at this point and the normal to the plastic strain direction. So this lies between the tangent plane and the normal to the plastic strain direction. If d sigma lies here, then this angle is greater than 90 degree, which means that this condition will be violated. But this condition can never be violated. This is an inviolable condition, which means that the only way that can be possible, always guaranteed, is when this normal surface to d epsilon p and this normal surface to n, or the tangent plane, are coincident, or in other words, d epsilon p is in the direction of the normal to the yield surface where the stress hits the yield surface. So if this is the situation, then this can never be violated. This can never be violated. Right. So what have we seen? We have seen that for this condition to be never violated, we must have the direction of the plastic strain in the direction of the normal to the yield surface. And remember, the yield surface is a function of the stresses. So therefore, the normal to the yield surface would be del phi del sigma. Okay. So we will come back to this later, but let's see the other inferences from Drucker's postulates. Imagine that your yield surface locally around this point is shaped like this. This is your yield surface. If this is your yield surface, then this stress state is an elastic stress state. It lies inside the yield surface. And then you go increase the stress in this direction and hit the yield surface when your stress is sigma. So then this vector times the d epsilon p vector is, so this vector is this, and this angle is again greater than 90 degree, which means that this condition will now be violated. Which again means that your yield surface must always lie below the local tangent plane, which means that it has to be a convex yield surface. So Drucker's postulates give me two very important principles from which I am going to build my mathematical theory of plasticity. These principles are that stability of the material, these are, remember, these are conditions that a stable material must obey. Stability implies that the plastic strain is proportional to the normal to the yield surface, and the yield surface always has to be convex. It can never be concave. We cannot have a yield surface which looks like this. We always must have an yield surface that looks like this. We must have a convex yield surface, and we cannot have yield surface with concave parts. Okay, so these are extremely important inferences, and then we will use this to further build our theory and then solve some problems. Now, these are the ingredients we need to build a complete theory. We already have a yield condition. We are dealing with perfectly plastic materials. And for the perfectly plastic materials, the radius of the yield function, as I showed in the animation before, radius of the yield function remains same. So the yield stress, the stress at which yield occurs in uniaxial cases is always the same, and they are also same in tension and compression. So this K is some kind of a constant which gives you the radius of the yield surface. As in the uniaxial case, we have a decomposition of the strain, the total strain, elastic strain plus plastic strain. So remember the stress strain relation in. So this is your perfectly plastic material. If you unload from here, this is your plastic strain, this is your elastic strain, this is your stress, and your stress is this two lines are parallel. So your stress is always given by E times epsilon E. So if you take increments of that, then d sigma ij, the increase in stress due to an increase in strain, will always be given byCijkl d epsilon kl E, and not E plus P, just E. That is just in analogy with the uniaxial response that we see. Finally, we have got the Drucker's postulate, which say that d epsilon ijp must be parallel to the normal to the yield surface, normal to the yield surface. So the normal to the yield surface is, yield surface, remember, is a function of sigma ij. So the normal to the yield surface will be del phi del sigma ij, and something parallel to this normal would have a multiplier d lambda, which is always greater than 0. So this d lambda is always greater than 0 because that will ensure that d epsilon ijp is greater than 0. So plastic loading is happening. So when d epsilon ijp is greater than 0, that's when plastic loading is happening, when your plastic strains are increasing. So this is called the normality condition, and the normality condition states that the plastic strain is parallel to the normal to the yield surface, and this is called a plastic multiplier. This is proved, this we have proved for a material that obeys Drucker's postulate, which is a stable material, and for such material, this rule, which is also called a flow rule because it gives the flow strain. This is also sometimes called the flow strain. This is a flow rule, and in particular it is called the associative flow rule. There are non-associative flow rules also, where the plastic strain is not normal to the yield surface, but those cases are not for stable materials. We are dealing with only stable materials, and for stable materials, associative flow rule is the only flow rule that we can have. So with these ingredients, with this 4 ingredients, we can build a complete theory of perfectly plastic materials, and then we will build it for hardening materials as well. We will do so mostly for the von Mises condition because that's what we are going to use, and that's what is popularly used for many metals. You must understand this, the role of this plastic multiplier. Plastic multiplier will be 0 when the material is inside the yield surface. So in the elastic zone, there is no d epsilon ijp. So if you increase the stress, you only cause elastic stresses to increase, elastic strains to increase. So d lambda is equal to 0 when sigma ij is inside the yield surface, and d lambda is greater than 0 when sigma ij is on the yield surface. Remember, the sigma ij can never go out of the yield surface. In a perfectly plastic material, it remains stuck to the yield surface. In a hardening material, if it goes out of the yield surface, it takes the yield surface, it pushes the yield surface with it. So phi greater than 0, this phi greater than 0, phi greater than 0 is not possible. Okay, so these are the ingredients, and now we will use the von Mises yield criteria to use these ingredients and derive what is known as an incremental stress strain relation. Incremental stress strain relation. You have to make a distinction here. In elasticity, we had derived constitutive models where we wrote this. Okay, there was nothing incremental about it. The stress, the total stress at a point is proportional to the total strain at a point of time. So the stress now is proportional to the strain now, no matter how you have reached here. But we cannot do that for a plastic case, or for a case which has elasticity and plasticity together. We cannot do it for the simple reason that the way you have now the way you have reached this epsilon k L, the way you have reached this epsilon k L is important to the overall stress that you develop. Whether you have reached it in one go, whether you have unloaded and reloaded in between, all these things will matter as to how much stress you are going to acquire for a given strain. So irreversible material is necessarily dependent on its history, on its loading history. So since it's dependent on its loading history, we will not seek, in general, we will not seek this kind of a relation. We will seek a relation between d sigma ij and d epsilon kl, and we call this elastoplastic. This may not be a set of constants. This may be dependent on the stress, and it will be dependent on stress. So if we get this relation, we have to then slowly progress, ask whether we are unloading now, we are loading now, and based on that, update this stiffness, find the stiffness at that point which is suitable for the kind of loading that you are doing, and then progress, keep on integrating this incremental relation to get the total stresses. So that is that process we are not going to talk about, but what we will be interested in is a incremental relation rather than a total relation. However, in certain cases where we can rule out unloading, remember this Cijkl is a bunch of constants in case of an elastic material. They can also be nonlinear. It can also be a nonlinear material, in which case Cijkl may be a function of stress, but the material is reversible, so it is independent of history. Whereas a plastic material is dependent on history because the unloading behavior and the plastic loading behavior are not the same. However, if we have a material which we are sure we are never going to unload, we are just going to load, then we can treat it as an elastic material, but a non-linear elastic material. But even in that case, we can have a relationship between the total stress and the total strain, a non-linear relationship, which looks pretty much like this non-linear relationship between the stress and the strain. And we will derive those relations a bit later. But right now, what we are going to do is we are going to look at these incremental relationships, and the incremental relationships will be between d sigma ij and d epsilon kl. Small increment in strain, how does it cause a small increment in stress? That's what we are going to look at, and we are going to look at for hardening, non-hardening, perfectly plastic, and then a hardening von Mises material.